Welcome to this video on boundary and mixed lubrication. I'm Roland Larsson from Luleå University of Technology in Sweden. The presentation here is mainly about boundary lubrication. I will talk a little bit about the transition to mixed lubrication, but if you want to learn more about mixed lubrication, you really need to know about boundary lubrication and full film lubrication. So mixed is simply the transition between the two regimes. So there are no real theories about the mixed lubrication that is different from the full film or different from the boundary. So you need to learn about boundary and full film to understand mixed. The outline is like this. I will try to describe the complexity of boundary lubrication. It's very much more complex than full film lubrication, I would say. I will mention the running in of surfaces because this is a very important phase of a machine surface or a bearing surface because most surfaces are running in boundary lubrication at the beginning, but then they run into more or less full film lubrication. I will talk about the PV number as something to estimate, can be used to predict the severity of the boundary lubrication, and I will talk about tribofilm formation. A short recap about boundary lubrication. The load is carried by the asperities in boundary lubrication, not by the hydrodynamic effect or the film itself like it does in full film lubrication. So load is simply carried by a few asperity contacts, like in a more or less like in a dry contact. The films are then also very thin. It's some kind of a tribofilm is formed in between the asperities. I will come back to that in this video. And since we don't have any hydrodynamic effects, the viscosity plays no role. Instead, the additives are very important. Some of them will be discussed here. For example, the anti-wear additive and the friction modifier and the extreme pressure additive. So, but the base fluid or with its viscosity still plays a role in a way because it's a carrier and it's a solvent of the additives, so it carries the additives to the asperity contacts. So viscosity may play a role in that way instead. Of course, in a contact where you have load carried by the asperities, there is a risk of wear here, and it's a risk of severe wear. So since surfaces are in direct contact. So in boundary lubrication, we really want to know when wear is occurring and when lubricated wear is occurring. But as we know, or as it has been shown over the years, that it's very difficult to predict this wear, or it's difficult to predict wear in general, but it's even more difficult in a lubricated contact because you have additional parameters controlling the problem. In that case, from Ken Ludema's work, we can see that you may need some 80 parameters or even more to determine the wear, and many of those 80 parameters are very difficult to estimate anyway. So there are no real good simple equations for boundary lubrication yet, I would say. Some of the important parameters are the local contact pressure, the asperity pressures, the temperatures occurring there, the strength of the material like hardness, the formation of protecting layers, the speed, load, viscosity. So this is the regime more or less where you can, if you can estimate the film thickness, then you can estimate if you are in the boundary lubrication regime at all. The surface reactivity is important, or how the wear debris is transported away from the contact could be important and very difficult to predict. The environment is important, and of course the surface topography. I recommend you to read this book also. It can be found on the internet. Coming back to surfaces here, and I want you to remember again what is formed on the surfaces. Starting with the base material, which is undamaged base material. On top of that you have some layer which could be a worked layer, where here you have, from the tribological contact, the microstructure has been changed due to the high pressures, high stresses occurring when another surface come in contact with this surface. And very close to the surface and relatively thin, you have a very much worked layer where the microstructure is completely changed. This layer has been melted due to the sliding contact, or could also have been occurring during the manufacturing of the surface. So it's a kind of remelted layer. On top of that you may have an oxide layer. The oxygen in the air has been reacting with the top layer and formed an oxide, and on that you may have a reacted layer by something else too. Could be an additive reacting with the surface, and on the top you have an adsorbed layer, a physically adsorbed layer, which is very thin. It's something like only one or a few molecule layers thick, and then you have the lubricant. Could be a fluid or a gas. So we need to remember this picture when we talk about boundary lubrication. What can happen in a boundary lubricated contact then? Well, if you get too high temperatures, then the surfaces may suffer from adhesive wear. It's like we normally distinguish between scuffing and seizure, where scuffing is like micro welding of the asperities. Since the temperature and the pressure is highest at the asperity summits, you may have reached so high temperatures that you rub off the reacted layers on the surface, and the two surfaces weld together on the asperity level. If you have too high temperature, that you actually create a welded contact in the whole or a large area of the lubricated contact, then you may have macro welding, and then we talk about full seizure, total seizure. That means that the surfaces may stuck completely, and you may also have too high contact pressure, and then you get abrasive wear. So that's that you form dents. Asperity of one surface dents the other surface, or may plow the surface or even cut the surface. And if you have some particles and wear debris coming from some of the processes, this may accelerate both the adhesive wear and the abrasive wear. The typical regime mapping to find out if we have boundary lubrication is to use the Strebeck curve and to compute the lambda number, the film parameter, the ratio between film thickness and surface roughness height. That is a relatively poor type of mapping, and especially for elastohydrodynamic lubrication. So some years ago I made this instead. It may distinguish between the different types of boundary lubrication and also full film lubrication. So I thought like this. This is a kind of a PV diagram also. So here you have pressure multiplied by the surface or mean slope surface roughness parameter. So pressure, this is the nominal pressure, and then we also know that the higher the slope of the asperity is, the higher the pressure. So in this direction we have something like local asperity pressure. It tells you about how high the pressures are. In this direction we have speed multiplied by viscosity, and that tells you a little bit about how good the hydrodynamic effects are. So then I thought at low pressures and the better and better hydrodynamic effects, then you have hydrodynamic lubrication. You don't have any deformation of the surfaces. But if the pressure becomes higher, you deform the surfaces and you run into the full film elasto hydrodynamic lubrication regime. If you reduce the speed or the viscosity, you run into mixed lubrication and eventually into boundary lubrication and even into kind of dry no lubrication if you have no speed and no viscosity or no lubricant at all. If you run in the boundary or in the mixed and increase the pressure only, then you may come into a wear situation, and which requires some anti-wear additives. Coming back to the anti-wear additives soon. While if you run at higher speed and come into the boundary lubrication, you may come into a situation where you need an EP lubrication, where scuffing or seizure may be a problem. This is not a perfect mapping at all, but it still gives you an idea about the difference between kind of mild boundary lubrication, a regime where you need anti-wear additives, and the regime where you need some protection for severe adhesive wear. Everything happens on the asperity level. So, and you may distinguish between 4 different cases of asperity collisions. So let's assume that we have an asperity here. We have it. It's base material, it's oxide layers, and it's some kind of reacted tribofilm layer here. And you have an asperity, a similar asperity here. You see that the lower asperity crashes into the upper asperity, and 4 things may happen then. In one case, it's only the tribofilm is affected, so you wear off the tribofilm, and after collision you just grow back the tribofilm, and everything is okay. That's a good thing. As long as you have the additives you need, it's okay. The second case is where you have only the oxide layers are removed here. So after the collision, the oxide layer and the tribofilm is grown back. You do wear the surface a little bit because you wear off the oxide, and you need to use some of the base material to form a new oxide here. But still, it's a kind of mild wear situation. A worst case is when you wear off the whole oxide layer here, and kind of naked surface come into contact with the other surface. Then you have a very reactive situation, and the 2 base materials, especially if they are made of the same material, they may weld together, and then you form this scuffing situation or seizure if it's the whole surface. So this is adhesive wear. Another situation that could happen is that the asperities are very much deformed, plastically deformed, or they may even cut off. One of them may cut the other one, and then you have abrasive wear, and it could also lead to a failure if it's severe. It also happens during running in, when you have plastic deformation of the asperities. If they have high slope, they may plastically deform, and they will be smaller next time they come into contact. So, and that is what is happening during running in. So, and I would say that in many cases a new surface always run in boundary lubrication or mixed lubrication the first time it's used, because normally you don't make the surface with asperities with low slope, because it's too costly to do that. So instead you are using a running in, and the running in is very important for the service life. So if you do it if you have a too rough running in, you may run it out more or less instead, or you may shorten the life of the surfaces. But if you do it correctly, you will round off the asperities and mechanically, and you may form a chemical tribofilm on the surface, which is protecting the surfaces. So then you end up with a protecting tribofilm and rounded asperities, which are very much easier to lubricate in hydrodynamically as well. So you may end up with a chemically protected full film lubrication contact. This is an example of a running in. So it's a ball on disc experiment. It's made by using electric contact resistance, and with that method you can estimate if you have a very much boundary lubricated contact, very much metallic contact, then this number is 0. If you have a fully separating film, then this number is 100. So here you have a full film lubrication. In this experiment, or in this example, 3 different surfaces have been used. One surface with a low surface roughness height, one with medium, and one with high. So this is the roughest surface. Then on the other end of the graph here, we also measure the friction. So you see here that this is the number of cycles. We talk about 120,000 cycles here. So it's a relatively long experiment, several it could be hours here. And you see that in the very beginning, 0 here is 0. In the very beginning, just after a few cycles, the friction goes down for the roughest surface. It goes down from 0.1 to 0.75 or something like that, very rapidly, and then it lowers, it reduces all the time, but becomes pretty constant already here after 20,000 cycles. The same goes for the medium roughness, and you can see some effect also on the smoothest surface. The electric contact resistance signal for the smooth surfaces goes up very rapidly, up to almost 100. So here you have full film already here sometime. For the rougher surfaces it takes a little bit more time, about the same time for the medium and the roughest surface here actually. So but after some cycles you have more or less full film lubrication. So this is a good example of successful running in. You had a very poor contact in the beginning here, but then you round off the asperities and the surface becomes slightly smoother. An important thing to remember from this example, and I suggest that you read this paper, is that the lambda parameter, the film parameter, hasn't changed very much. It's almost the same before running in and after running in, but it's other features of the surface roughness that has been changed. It's typically the summit radius has been much bigger, the slopes have been a little bit smaller. So and this is very important to understand, and this also makes the film parameter, the lambda parameter, less useful for EHL. But this is how it looks like in a running in experiment. All right, I realized that this video about the boundary and mixed lubrication will be a very long one, so let's end part 1 here, and I will see you soon in part 2. Thank you very much.